general. Something like 1 plus 3 is equal to 4, which is 2 squared. 1 plus 3 plus 5 is equal to 9, which is 3 squared. So we're trying to prove that that continues on forever. Yeah? Okay. So we're going to use this TAPAS method, test, assume, prove, assumptive step. Okay? So the first thing we're going to do is we're going to test. And when you test for the lowest, like the base case, the lowest value n could be. So what are we going to test for? What's the lowest value n could be? So we look at what's our number system we're dealing with, positive integers. So test for n equal to 1 is the lowest one we can go with. Okay, so I'm going to test for n equal to 1. It's almost too obvious, but the left-hand side of this would be what? Just 1. Well, you can use the formula if you like. It gives you a formula for odd numbers. 2 times 1 minus 1, which equals 1. The right-hand side of the equals is 1 squared, which is also 1. So the left-hand side equals the right-hand side. Okay? Better get my correct. And then 3 dots in maths, what does 3 dots mean? So. Therefore, statement is true for n equals 1. Not rocket science, almost too easy, but you have to do this step. You've got to prove it was right in one case. What's next then? So T for test, A for assume. Assume n is equal to k. So we assume in this step that it's true for assume true for n equal to k. So we're going to assume it's true for another number. And then afterwards we're going to prove it's true for the number after that. The domino effect. So assume it's true for n equals to k is just a rewrite of this with k.
Mr. Collins,
Hi.
your left-hand side,
Yes.
why does it work for all n? Because if you just, wouldn't you have to do 2n minus 1 plus 2n plus 1? Don't they have to be consecutive odd integers for it to work? Like if you just put in, like for example, if I just put in 6 into n, like you did, you just put 1 in, then I would get 11. But 11 is not equal to 36.
No, 11 would be, remember we're adding up. 11 plus 9 plus will equal 2 squared. That's what this is saying. It's an addition, it's a sequence, or a series, sorry. It's not just the one term. So the next term in the sequence is not looking at 3, does that equal n squared? It's 1 plus 3 does equal n squared. The number of terms added together equals n squared.
But then is the formula just 2n minus 1, or is it 2n minus 1 plus 2n plus 1? When you prove.
Oh, we'll come to that. For now, you're going to be confusing people, but we can come back to that. Okay, so we're assuming it's true for this. And then we're going to prove it's true for the one after k. Okay, so we've done TAP. We're going to prove it's true for k plus 1. So what does that look like? That looks like 1 plus 3 plus 5 plus this one plus the next number. 2 times k plus 1 now minus 1. Did that answer your question? No. So it worked for up to here. All right, we don't know if it works for up to here, but we're going to prove it for this one more than there. So k has been replaced by k plus 1. And that will equal what? So everywhere there was a k on the right, I replaced with k plus 1, and then I went to the next term in this series. So I got to prove that. Now at some stage in the proof, and this is what proof by induction is, we've got to use something called the assumptive step. which is using this statement in this statement. So we can see from here, this bit is equal to what from the assumed true bit? K squared, yes. So K squared now, instead of all of this, we know that, well, we assume that these two are equal, so that all of this bit is now replaced by K squared. Now you're always going to do that. You're always going to use the assumptive step. Some people say from assumptive step, or just write assumptive step. So all I've done is now created something like we did in the starter thing, that I need to now prove that the left-hand side equals the right-hand side. If I do that, then I've proved the whole thing. So I'm going to go up to the top of the board now and finish the proof step. So I'm going to rewrite this up here. K squared plus, perhaps I'll multiply this out. We get 2k plus 2 minus 1. We're just continuing on, yeah. No, we're continuing on. Just the assumptive step is in the proof. Notice I haven't really put the box around it. It's all part of the proof. It's just to remember to do it, the A. Okay, so tidy this up a little bit. I get k squared plus 2k plus 1 is equal to k plus 1 squared. And if I factorize the left, what do I get? You can put in an extra line if you want, k plus 1 times k plus 1, or you can just do this, because that is that factorized, isn't it? It's perfect. Square. And that's it. The left-hand side equals the right-hand side. So you're always going to be working on this left-hand side all the way down to get it to equal to the right-hand side by using this assumptive step where you replace this part of it with this part of it. Yeah. Yeah, there's more than one way, but the question may ask you to prove by induction. You can prove sometimes like infinite series, definitely, yeah.
So what's induction?
Okay, it's this process, yeah. Let me finish the thing, because we're there. Because you must write a statement at the end. And the statement goes, and I will write this from my notes, because I usually forget. Since true for n equal to 1, and true for n equal to k, make more space, implies true for n equal to k plus 1.
So you'll write this.
Therefore, you're going to write this. Therefore, I'll write therefore. Therefore, true for all n. Well, this is specific to this example, but whatever, maybe it's not all positive integers in the one you get, but that is the statement. Now, why is this the statement that I use?